Good evening, everyone. So, we welcome you all on the day 13 of our FDP, sponsored by EICT and MIT, that is on fundamental of smart grid. So, today's topic will be hierarchical control techniques in hybrid AC/DC microgrid, followed by simulation and case study of AC microgrid. So, sir is with us. Now, sir will be teaching these two topics to us today. So, we welcome you, sir. Over to you. Thank you.
Thank you, Manmohan. And today we'll be talking about, welcome you all to this mighty sponsored course on fundamentals of smart grid. As in today, we covered almost all the basics and we are halfway through. Today we'll be getting into deeper AC/DC microgrid specific to hierarchical control techniques. The biggest challenge today that whenever any microgrid which has been connected to a uh, main grid, we connect both the AC grid and DC grid using a interlinking converter. Now, the interlinking converter play a very important role to manage not only the power but as well as the energy of the whole microgrid. The question comes whenever the grid, the microgrid is detached from the main grid through ILC, when you say islanded mode of operation, so probably it is completely out. And again, after some time, we can move to the normal grid. So from a voltage regulation mode to a current regulation mode, we shift actually with the grid, without the grid. So who does everything, how does it happen? You disconnect automatically, you connect automatically. There are many devices. Today, if I ask you what are the components of a AC/DC microgrid, we'll start with from AC load and DC load. Then we move to AC generation, such as we have main grid. Then we will have actually wind generations. We will talk about actually bit of diesel generators are also connected today, though we do not want to have it. And then you go to DC generations like PV and batteries. So, for a systematic operation of the whole system, one need to understand how those control mechanism at each and every device level and at grid level, device level, bus level, and then to the grid level. So this is what we'll be talking today. So very quickly, we'll try to understand what is smart grid. We know it, but let us repeat it today. So smart grids are being developed as the next generation power system, the future advanced distribution management system, so-called ADMS. These smart grids encompass interconnected microgrids, especially at the distribution level. So we talked about topologies, we talked about a basic pilot, but today we are talking about a real microgrid, and there's not one, but there are multiple microgrids are in place. So the microgrid can work in grid-connected or standalone operation modes, particularly the standalone operation, although may only for very limited period, can provide improved reliability to the smart grid. Okay. Now there are many generation technologies we need to understand. So one is wind that we all are very sure, photovoltaic, wind, micro hydro. As on today, we haven't talked about micro hydro is one of the generation source for microgrids. So micro hydro could be one of the source. Any one of you is clear about what is micro hydro? Why we call hydro power plant is known, but what is micro hydro? Micro, no idea. Okay, let me see. When you say there is a power generated from waterfalls, is my hydropower plants, okay? But if I say very low head, means let's say some uh, 50 feet, 60 feet, small, like a waterfall. If you go to Sri Lanka or if you go to Kerala, okay, uh, many areas where the waterfall is not very, very heavy, but you can run some small turbines, even Ladakh. Many people use, small plants actually to operate with a very low headfall. Okay. So it's not like a megawatt level, but maybe let's say 5 kilowatt, 2 kilowatt, 3 kilowatt, 10 kilowatt, 50 kilowatt. Plants can operate with some. There's water keep on falling. You put a small motor and it will generate power and electrify the whole village. And they are actually known as micro hydropower. So it may so happen that you go to an area which is completely isolated and you can have a grid where not only PV, but you can have micro hydro plants also part of the microgrid which caters to the whole local load. Please.
Overhead.
Yes, I mean,
High-rise buildings.
yeah, it is possible. It is possible. And if you read some of my articles where we attempted, we have already done it before 10 years, these problems, all right? There actually we very nicely, what we have done, actually we have taken a well because we realize well is a very common concept in southern and eastern India. North, it is not that common. But in eastern India, even today, even in my home, you'll find a well today.
In our villages.
Village, but I'm saying each home. If you go to my street, each home will have a well. All right. But nowadays they have put pumps actually because no energy to pull it actually. But it is there actually. So what we realize that anyway we are pumping that water to the top and we use some time of day tariff where we said that water once it is taken, assuming that there is cheaper energy available to me, then I will take the tank, vacate the tank by putting the water in the well again. Like a pump storage power plant concept applied to home actually. Okay, so you can make money even at home. So there, this water will fall in two micro wind turbines, which are situated within the well. So it will go to the well by rotating the fans and then fall. And then you get electricity out of it. Are you clear? Very, though it is in elsewhere, but people have appreciated that word. Okay.
So this conventional hydro plants, they are conventional source.
They are
Not renewals.
no, they're renewables. They're considered, but there are two things. But they're not into microgrids, no. They're so heavy by itself. Let us say we have Tehri Hydro. So Tehri Hydro is a hydropower project, but they are not part of the microgrid.
So that is classified in renewals or conventional?
This we say actually hydro. We don't say actually it is. We say it is a hydropower project. If you wish, you can consider it conventional. If you wish, you can use it as a green. It is, but saying renewable completely is not a good idea. But we can certainly say that micro and mini hydropower projects are part of the renewable for sure. So many cases, hydropower projects, though it is considered to be green, okay. So we can include as a renewable. Many times we say hydro, including hydro, the renewable contribution is close to 13%. Like that we write. Excluding hydro, the renewable contribution is 7%. We write like this. Okay. So by calling hydropower project as a renewable power project is not a wrong statement. Wrong statement, but it also sometimes misleading people by saying the true renewable contribution what is expected. All right. So that is fine. So micro hydro, then why hydropower projects, dairy hydro is not part of microgrid? Because it's not it is so big actually. So smaller hydropower projects, which are actually micro level, which is in few kilowatts, similar to a diesel generator, will be considered as a part of the microgrid. Okay, because a hydropower project, all the energy is coming to the grid. Okay, there is no scope of disconnection and connection. Everything will come to the grid. So they do not get connected to a microgrid because microgrid voltage levels are extremely reasonable. So then we talk about biomass is once again considered to be a renewable part and then geothermal. Okay. um, geothermal, and then ocean wave and tides, which is again not very big in quantity, but we can consider fuel cells, the traditional rotational machine-based technologies such as diesel generation and energy storage. So many times, when you talk publicly in global platforms, they do not consider diesel generator as a part of the uh, they do not encourage it because they say, oh, this is an analysis where we are not going away from the renewable energy sources. So diesel generation is perhaps one way we are stopping thermal, but having diesel in the microgrid and calling it as a renewable integration is not a good idea. But considering Indian context, where every here and then we have millions of actually diesel generators, even for a army camp on top of the hill, cannot survive without a diesel generator. And they can have reasonably PV also. So it may so possible that a microgrid of a army can operate with a combination of PV, battery, and diesel generator. And that is going to be the one of the best combination if you see practically. Robust and realistic. So that means you take all the PV. If it is excess, you charge the battery and discharge. But otherwise, anyway, diesel, because it's completely isolated, isn't it? Kargil cat, actually, you cannot have main grid available. Okay, so there you have to go with diesel generator. And I have been told that trucks of oil is being taken up to the hill, running actually, especially do you know this um, antennas, the big antennas for communication, they need also energy, and they are continuously run by diesel generator because no grid connected. And if you can have a PV plant next to the tower, that would be a great. So today, a lot of research happening for PV and diesel generator catering to the communication towers. Okay, because if you see some hills, somewhere there is a tower and there is nothing, no energy available. So that energy must go from your telephone towers. No? They all require some energy. So they put a diesel generator always. So if you can replace the diesel generator by some PV, so the capacity of diesel generator will reduce. All right, good. So there are so many things actually now. We are actually making this unit now a little complicated compared to the previous case. So now we are getting into a real scenario today. And you all know that we talked about AC-DC microgrids, and it has both AC subgrid and DC subgrid interconnected by Paul Phoenix interface. And you could see that interlinking converters are available, and then you have a AC section, and then you have a DC section, and which is connected to the utility grid. Now, when I talk about different components of AC-DC microgrid, there are two major components. One is physical component, the other is actually communication requirements. Okay, physical components, we have AC microgrid, we have DC microgrid, interfacing converters, sensors, and controller. And when you move to communication requirement, it is your networks, protocols, intelligent electronic devices, IEDs, Internet of Things, IoT devices for network hybrid microgrids. Okay. So I'm not getting into the diagram as such, but one thing is very clear from this. You can see you do have a AC microgrid 1, you have a DC microgrid 1, then you have DC microgrid 2 and AC microgrid 2. Now here I like to highlight certain concept of true implementation of microgrid nature. One, isolated microgrid implementation, control, connected with grid, isolated, everything is fine. But when you have multiple microgrids, imagine I do have electrical, mechanical, and civil engineering in an institution. Electrical engineering department could be a microgrid, mechanical is another microgrid, and civil is going to be the third microgrid. Now, can all three of them be connected? As on today, it is not. So that means the energy exchange takes place between a microgrid to the main grid, between a microgrid to the main grid, between microgrid and the main grid. But the microgrids are not connected. They cannot. For example, if the microgrid 1 can charge the battery of microgrid 2, or can microgrid 2's diesel generator charge the battery of microgrid 1? Or the PV of AC microgrid, DC microgrid 1 can charge the battery of AC microgrid 2? So many things can happen, no? I have excess, I have nothing to charge, my battery is fully charged. Can I take this energy to another microgrid? Today it is not possible. So probably that also need to be explored. So multi-microgrid concept is very important. And to do that, both the microgrids, all the DC microgrids and AC microgrids must communicate to each other. How do I know I have access? How do I know that my battery is charged? Am I right? So the control protocols become very, very important.
So this IoT and CPS are almost same.
IoT and
CPS, cyber physical systems.
they are different now. IoTs are basically, they're the devices. For example, I can say my smart meter wish to switch off my air conditioner during peak load. Okay? Or I like to charge the electric vehicle when the electricity is at its off peak. So for that, a command has to go to that charging port, no? So there I will have a IoT device. That will sense the command from the smart meter. And the device itself is known as IoT. But when you talk about cyber physical layer, it is much bigger than actually IoT device. IoT device become a part of the cyber physical system. Okay, good. So type of converters employed for interfacing. So first is interfacing converters to link the DC microgrid, DC microgrid and AC microgrid or utility. Interlinking converters, generally referred to as ILC, works on the principle of equalizing DC side per unit voltage with AC side per unit frequency. Because the DC side don't see any frequency, okay? So the responsibility is actually the smooth power exchange takes place between these two through the interlinking converter. Then you have back-to-back converter also. Okay, one more interlinkage back-to-back converter, generally referred to B2BC, that is back-to-back converter. It employs references setting control on both sides, that is PDC and PSC, to be exchanged are set as reference to enable power flow between the DC and AC microgrids. Okay. Now, what happens normally in an AC system? We have two voltages, VI angle theta I, VJ angle theta J. So because of there is a difference in magnitude or in angle, we'll have a real and reactive power flow between these two buses. Similarly, for a DC system, we'll have V1 and V2, and depending upon the impedance of the line, or resistance of the line, we will experience some real power flow. But here, what we are saying actually, the PDC and PAC can be, exchange energy from DC bus to AC bus through your back-to-back converter. Now, just quickly look into the structure of hybrid AC-DC microgrid. We have already discussed, I am reiterating today. So as you could see, there is a AC bus, very simple AC bus, hybrid microgrid, two different structures. You have utility grid and there is a AC bus. Everywhere you convert that AC power to DC if required, or DC sources will convert to AC and connect it. So there is only one bus, that is my AC bus. Okay, very, very popular structure, very popular, very realistic. Okay, but bit of losses because of multiple conversions. So to avoid that, what you are thinking, we are going for a DC bus and a AC bus concept instead of having multiple conversions. So there actually we will have many interfacing converters, And what people also say that, in DC coupled hybrid microgrid, distributed generations and energy storages are connected to the common DC bus, and an IFC is used to link the DC to AC buses. Whereas in the first case, in AC coupled hybrid microgrid, all right, various DGs and ACs are connected to the common AC bus through their interfacing converters. So if you majorly focus on AC bus, then you concentrate on the first structure. If you're focusing on a DC bus, then the second architecture become more suitable. All right. Now, if you combine AC-DC as a hybrid microgrid, as previously you have seen, this is my hybrid microgrid. There's one more structure, is this one, where in a AC-DC coupled hybrid microgrid, AC-DC coupled hybrid microgrid, distributed generations and energy storage are connected to DC and AC buses, where these buses are linked by interlinking converters. There are many important features and challenges. So what are the challenges of this structure? The main challenge is to manage power flow among all sources distributed throughout the two types of subgrids, which is certainly together than previous effort developed for only AC or DC microgrid. So this is certainly a better structure. All right. The mode of operation could be grid-tied or standalone, that is autonomous, and the control techniques in hybrid microgrids generally are based on a true control mechanism that you have already learned. Now, one important part today, we said that for any microgrid, we need a storage technology, and we have done it. But also it is important for the benefit of the readers, or especially students or participants of this course, that what is the need of the storage in microgrid? I may say, no, I do not want any storage, because storage is an expensive mechanism. Why do I need to have a storage? So first is about the intermittency of the renewable energy which has been integrated to the microgrid. Due to the intermittency nature of renewable energy sources, other energy sources, the storage elements are critical part to enable the standalone operation of microgrids or to smooth the microgrid power during grid connected operation. Storage elements can be classified into two categories. One is capacity oriented energy storage and excess oriented energy storage. We'll discuss what they are. So today, basically, all of you, so my request to all the students to concentrate, because it may look like it is exactly same what you have learned, but it is not so. We are slowly getting deeper and deeper into microgrid studies here. So once again, I repeat, due to the intermittent nature of renewable energy sources, that is, both PV and wind, they do not continuously produce energy. Am I right? And the frequency of energy production is keep on varying. And even some other energy sources, the storage elements are critical, because if you like to meet a load of, let's say, 10 kilowatt, and if you generate energy 6 kilowatt, 20 kilowatt, 14 kilowatt, 2 kilowatt like this, then how do you meet a load of 10 kilowatt? Because your generation is keep on varying, which has never been more or equal to 10 kilowatt. So that case, we want everything to be stored, and the load will be catered by the storage device all the time of 10 kilowatt as and when required. So that means because of this intermittency, I cannot have a standalone system where loads are connected against a intermittent generation source. If I connect these two, they never match, okay? So that's why storage is important. And the storages are two different types based on its application usage. One is known as capacity-oriented energy storage. The other is actually excess-oriented energy storage. So capacity-oriented energy storage does not have fast response time, and they're used for long-term energy balancing to buffer out low-frequency power oscillation of distributed generations output power and compensate intermittency of renewable energy sources in the microgrids. Batteries, pumped hydroelectric, compressed air energy storage, hydrogen storage are the type of capacity oriented energy storages. However, when I talk about excess oriented storage, devices have fast response time, means very quickly, and they're responsible for short-term disturbances in microgrid. By providing the high frequency component of power, they can supply or observe the high power transients with high power density, such as flywheels, supercapacitor, superconducting magnetic energy storage are considered to be access oriented storage devices. All of you, please try to understand the very basic way to understand I can have a battery in a renewable energy microgrid, renewable energy integrated microgrid to make sure that the intermittency is being taken care. However, for fast frequency, quick action, we can have supercapacitors, which is popularly known as the access-oriented storage, can also be used depending upon the application type. Good. So how do you manage the microgrid? So there are the two different type of managements. Once again, I repeat, now today we are getting deeper into deeper. Previously we say energy is being managed, but today we'll talk about actually two different types of energy management. Earlier we said there is a storage, but today we are talking about what are the types of storage they are. So critical aspect of the operation of such a hybrid AC-DC microgrid is the control strategy and power management scheme. So we have seen the diagram where we said we have a bus, we have many devices. As I told you, how we are managing power, the load will be met by my renewable. If not enough, what I do, I go for my storage. If the storage is not able to manage, then I go for the main grid. Am I right? And if the main grid is not there, if it is in islanded mode of operation or standalone mode of operation, then if the battery is not able to cater, then I have to disconnect the load. That is what I do. So critical aspect of operation of such a hybrid AC-DC microgrid is the control strategy and power management scheme, which are essential for providing operation in both grid connected and standalone operation modes. In microgrids, by considering control tasks and time scale, the management of microgrid is divided into power management and energy management. What is power management? The objective of short-term power management strategy is to affect the instantaneous operational conditions towards certain desired parameters such as voltage, current, power, and frequency. The power management strategies include voltage and frequency regulation and real-time power dispatching among different power sources in the microgrid. Now, what is energy management? Because power means just you match the power, okay? In case of energy, these algorithms is matching the total power production to the demand in an optimal way, means the whole energy, with emphasis on desired and longer term outcomes, factors like fuel cost, capital cost, maintenance cost, mission profile, lifetime are part of your energy management program. This we have already discussed, but the mechanism is slightly different. AC coupled hybrid microgrids are two types. Either sometime it is grid connected or it is standalone. When it is grid connected, there are two varieties or two different types of grid connected mode. One is dispatched power output, the other is undispatched output power. What do we understand by dispatched output power? Where DGs and energy storage dispatched power control mode or power balancing. In case of undispatched output power, DGs MPPT control mode. DGs operate in MPPT mode, and AC's energy devices are typically on the charging. All right. So we are talking about what mode actually my storage and DG operate in a particular control mode. Now, when it is standalone, main grid is not there. DG and storage energy, AC bus, voltage, frequency control, and demand power sharing by either troop method, or it could be a master slab, or it could be power balance using model predictive method. So these are the three different control strategies we normally adopt. Now, power management strategies of the DC coupled hybrid microgrid, which is further complicated, which is one is grid connected, the other is standalone. Grid connected, again, we have dispatched power output and we have undispatched power output. So when you say dispatched output power, means my IFC of the DC link voltage control mode, DGs and ACs dispatched power control mode. In case of other type where DG and AC DC link voltage control mode and IFC will be in the power control mode. Okay, so we can have power and voltage and power depending upon your choice. And in case of undispatched output power, IFC DC link voltage control mode, DGs operate in MPPT mode, AC is typically on charging. Now in case of standalone, when you say DC bus voltage control, or AC bus voltage control, depending upon AC-DC microgrid strategies. In case of DC bus control mode, DGs and ACs, DC bus voltage control directly. That means droop method or indirectly a power balancing method is being used. Now, in case of AC, the IFC AC bus voltage will be at a control mode. Okay, so these are basically we are defining which variable become a control mode and under what the circumstances is a question. Now, this is the third, more complicated. All right, AC-DC hybrid, because three, always please remember, we had a case one, case two, case three, DC bus, AC bus, AC-DC bus. Okay, so in case of third, again, dispatched output power mode and dispatched output power mode. If I see now dispatched power mode again are two types, where actually voltage control mode for your ILC DC bus, then DG and AC is on a AC bus coordination with DG setting on DC bus for providing dispatch power, or I can get into DG and ACs on DC bus DC link voltage control mode, ILC and DGAC on AC bus on dispatch power control mode, and ILC could be in power control. Similarly, in undispatched, it is ILC DC link voltage control mode. DGs, both AC and DC bus will be operated in MPPT. All the PBs connected to either DC or AC bus, both will be in MPPT mode, and AC is the storage, both AC or DC typically in a charging mode. It's basically the same philosophy. We are keep on adding actually DC, AC both. Okay, coming to standalone, we have a DC bus voltage control mechanism, we have AC bus voltage control mechanism. In case of DC bus, both DG and ACs on DC bus, DC link voltage control directly. In case of AC bus, DGs and ACs on AC bus, AC link voltage control directly. So finally, the ILC and AC link voltage control mode or DC link voltage control mode or power control mode that you can operate both the scenarios. Now, this is moving to the power management during transition. Very, very important, my dear friends. Please concentrate. Power management during transition between grid connected and standalone operation mode. Now, what is happening? Previously, we realized, okay, fine, I have a microgrid. This is how it is to operate. Now, I'm assuming my microgrid is going out of the grid, again coming back to the grid. Going out of the grid, again coming back to the grid. How this is possible? Isn't it? What kind of control switches? Now, operation mode could be two types. Grid connected to standalone mode. Means the microgrid, grid connected, suddenly switching to a standalone. Or it was standalone and moving to a grid connected mode. So these are the two mode of operation. The first one, when it is moving to a standalone mode, switch off control strategy from current or power control in grid connected mode to voltage control in standalone mode. Okay. So power mode to voltage mode in standalone. Now, uniformed control strategy in both grid connected and standalone mode. Now, when you're moving from standalone to grid, what will happen? From a voltage control to power control mode, you have to shift. Previously power to voltage, now voltage to power. Switch off control strategy from voltage control in standalone mode to current or power control in grid connected. Right? So always when we are at standalone, we are at actually voltage control mode. When we go to grid connected, we go with power or current control mode. Uniform control strategy in both standalone and grid connected mode is very important. But when you move from standalone to grid connected, synchronization play a very important role. Along with this moving from actually voltage to power control or current control, we also make sure actually they both are actually synchronized. So synchronization of two types that I've already discussed in my video yesterday, where actually yesterday or day before yesterday, I think synchronization we discussed yesterday, day before yesterday, okay, where actually passive synchronization and active synchronization type of, synchronization can be adopted. Now, classification according to types of control for energy management in AC/DC microgrid, there are three mechanisms. We all know it. One is decentralized, centralized, and distributed method. Though we discussed a lot about it, I'm not going to spend more time, but this diagram I brought in to make sure that there is a centralized communication network. In case of decentralized, there is no communication. In case of centralized, there is a communication. And in case of, distributed, we do have also communication, all right? But if you see centralized communication network connecting to all three, but in case of distributed, I think there is no centralized control, but everyone is connected.
One to one.
Yeah, yeah. So this is how the types are. So in case of centralized, distributed, or decentralized, in case of centralized, communication network is needed. Central node or operator, access to global variable, problem of single point of failure, not reliable, okay? And decentralized, we need communication network is not at all required. Control through local variables and global variables are inaccessible. Now moving to distributed one, communication network is needed, peer-to-peer communication, lesser communication channel, then centralized control. No problem of single point failure, access to global variables. Here we can look into equalizing voltage and frequency in per unit between two buses, okay, AC bus and DC bus. So interlinking converter with the decentralized method. So in this method, interlinking converter mostly operated based on the Drupe law. That means you can see the structure of a AC microgrid, the structure of a DC microgrid, and you could see the structure of the interlinking converter, which is connecting both DC grid to AC grid. If someone is in the process of developing laboratory models for AC/DC hybrid microgrid, so probably these configurations will be of great help. Now, if you see the Drupe law, which is quite simple, we have DC side, we have a AC side. It's a very interesting philosophy. In the past, we talked about Drupe method, but for DC grid separately, for AC grid separately, for multiple DC grid separately, for multiple AC grid separately. But for the first time, we are talking about a DC-AC hybrid microgrid along with the interlinking converter. So what happens in case of DC side, you have voltage versus P, and in case of AC side, it is frequency versus P. So we have to take a point which is common to both the side where the V and F are considered to be fixed. So that's what actually we call interlinking converter is responsible for the voltage from the DC side and frequency from the AC side, because this is how actually we control. So relationship between P and V, relationship between P and F, and P become common both the sides. So F and V are the y-axis variables. So we'll take a point where some F and some V, they have to lock. And through that Drupe, anytime the frequencies vary, the V also will vary accordingly from the DC bus. So DC bus V and AC bus F, they are locked. And if you like to have different combination, then you can adjust your Drupe in such that, okay, you can have multiple frequency and multiple voltage matching between two grids for interlinking converter. This is a very, very Drupe control law, a brief overview, very, very important concept. Now, going to hierarchical control architecture in centralized method, here we haven't left anything. Almost everything is there. So this is more or less I will take, this diagram has been designed for Indian grids, okay, and where we have taken consider actually diesel generator. I still remember those days. I said, why do we follow Western world microgrid model? We have to be truthful that in India, if diesel generator is very commonly available in all my microgrids, so let the microgrid speak loud and clear that there is a diesel generator connected. Why do you sigh off? The whole world is using diesel generator, but in microgrid architecture, you will not find diesel generator, excluding our publication, most of the cases. Okay, I said, no, you do it, and then you see battery, solar, PV. And actually, few authors actually have very transparently connected diesel generator to microgrid. But whenever it has been presented in a common platform, people has, issues that why is bringing actual diesel generator to microgrid, because the global community is not ready to accept diesel generator can be part of the microgrid family. I get your point. But this is the truth. Truth is that diesel generator cannot be excluded from the microgrid family as on today. Okay. But they believe that if you have a battery, diesel generator can be avoided. That is true. But until unless you have enough renewable available, I think this is also not going to work. Am I right?
If it's already there, then we have to consider.
Yeah. If you're already using it. So this is what we do, and this you can see the slower control loops. Second two. So there are three different layers. But this is very important diagram. All of you please concentrate. So first of all, you have a grid. A grid is operating like a switch, islanding or grid connected mode, and grid mode or island mode. And then you have moving grid to islanding or islanding to grid. So when you come from islanding to grid, there is a synchronizing capacity. So the left top corner rotational diagram is very clearly talks about the operation mode. Grid mode, islanding to synchronization become grid mode. All right. So this is the circle of cycle. And then you have the main grid with me. The main grid is like a substation transformer of 11 kV or 33 kV. And there actually I get my AC bus. The transformer output is my AC bus. Okay. So you can see the AC bus clearly. Then you can have AC loads. You can have batteries. You have solar PV, you have wind turbine and diesel generator. Now you can have a DC bus by interlinking converters. And the DC bus again can have actually PV panels, batteries, computing loads and electric vehicles. So this is very, very crystal clear. And you have three different, all of them actually now, all the converters, they are connected to a control architecture that is known as popularly a hierarchical control architecture. So we have actually tertiary layer, secondary layer and primary layer. So tertiary layer actually we do, it is the slowest one, then slower and then fastest. So first actually we concentrate on tertiary, then secondary and then primary. So primary is very fast, okay? So first what we do actually grid operator, energy market, power exchange, whatever you like to do, balancing how much energy, unit commitment, economic dispatch, demand side management, everything you do 15 minutes, 20 minutes. You have decided, very good. Now we move to secondary layer, where actually power quality, synchronization, restoration, all the activities, and finally the primary, where it is the fastest one, PQ control, all those islanding detection, protection, BIF control, everything is actually coordination will be possible. So if you see ILC with distributed control methods, it is very interesting. You have actually AC line, okay, both the lines available to me. And we have communication network for both, okay. And we have actually there is a small actually error here. Can you identify what is that error? DC, so that is where the DC load. So, am I right? So the blue one is actually DC line. Okay, so there the right corner could be actually DC line instead of, there is a small typo here. Please correct it to AC. AC, the blue one actually instead of AC line it becomes DC line. So you have a AC grid, we have a DC grid, and then we have ILC connected. AC side is talking about P and F. DC side is talking about V and P or V and I. Okay, and then we actually have communication between these two grids, and finally we have a group control mechanism. We have primary control, we have secondary control, and finally we settle to a rated steady state operation. Now coming to a conclusion of today's talk, decentralized methods use local variables for control. However, due to unavailability of global variables, the method may suffer from inaccuracies in accurate power sharing. Centralized technique overcomes the inaccuracy issues, but at the cost of higher communication cost. Also, it suffers from single point of failure. Distributed technique utilizes reduced communication channels. It offers the similar performance as centralized, but with reduced cost by enabling peer-to-peer information exchange. Now we can also focus on different other architecture of hybrid microgrids, additional DC microgrid, additional AC microgrid, and potential research direction is slightly something different. I think if someone is really interested to get into cyber physical system and malware, though it is not purely power engineering, but someone who is good at computing and a cyber security expert, being an electrical or power engineer can do wonders today. To me, a person who will be successful in power engineering who has the capability of computing capabilities. Okay, if you see, you know load flow, all right? But optimal power flow is purely a mathematical problem. It's a, so today in the US, who will be paid the maximum salary? The power engineers, those who work on energy markets. So those who know good at mathematics, those who work on, because they make money. Okay. Stability experts work in the lab only. But energy market people actually really get a lot of revenues. In Western world, people see who is bringing what to the desk. Similarly, today cyber experts are actually very well respected because they can protect your system. And today, like, if I talk about a electric car manufacturing expert, is not that it that is too much popularity is not there for you. But if you're making a drone today, probably it depends on time. And if you have a technology to stop the drone not to operate through a cyberspace, then you are further great. So you are doing less work if you see you have no equipment in your hand, but your the ChatGPT is more powerful tool. AI is a more powerful tool than anybody else. Space scientists are nowhere with AI technology. AI engineers can stop your spacecraft to even take off. So it depends on time actually how the things go. And I met a gentleman, he was mentioning that, the way we have garbages in the earth, similarly, garbages are also there in the space. So there is a startup who is now working on collecting those garbages from the space. So you'll go and catch those garbages and come back. What is that garbage? Is one more satellite. So you will go there, collect it, and come back. It's a big engineering. Yeah. Non-working, already dead, but they're simply rotating now in their own space actually. So there are millions of truck-size satellites are floating. And what will happen? Traffic today it is fine, but one day will come, the space become congested. No, so I like to go for a satellite. They will say no space here, already congested. So we'll instead of going left or right, we'll come up and down, but again that will be congested. Isn't it? So imagine, and so it will be a very interesting. So self-healing power systems, cyber vulnerabilities, malware detection, mitigation, and resiliency become the future of power system engineering as of now. There are many references, but I will strongly recommend references, especially the eighth one is quite interesting. I would recommend everyone to read it. Thank you very much. And without, we'll get into simulations and case studies. Today we have examination from 700, right?
Sir, they can do it anytime. Can continue.
No, you will continue, yeah. So when we get into microgrid modeling and simulation, what we are talking today, before we go for, these are all fine, you studied, you experimented, but before you go for real-time implementation in the field, whatever we have learned is not enough. For lab level, it is okay, but you have to now getting into the field. So what are the things need to be done before you get into the real-time deployment of AC/DC microgrid? So detailed modeling and simulation of the microgrid system helps to conduct rigorous analysis and identify key challenges and feasible solutions before their physical implementations. Electromagnetic transient EMT simulators like real-time digital simulator RTDS provides a suitable platform for detailed analysis of power system transient in the time domain from DC to kilohertz frequencies commonly found in power tonics converters. The advantage of real-time simulation for microgrid modeling and simulation application include continuous real-time simulation and hardware-in-loop simulation. Continuous real-time simulation is a kind of simulation study only, but do it in a millisecond level actually in a continuous mode. And hardware-in-loop simulation where you create a HIL exploitation. So in case of continuous real-time simulation, microgrid analytical studies can be performed much faster than with offline simulation platforms. Since the simulator operates in continuous real time, the simulated system can operate in a manner similar to the real microgrid system. As the simulation parameters are modified and contingencies are applied, the user can watch the microgrid system respond in real time. Now, in case of your HIL, that hardware in loop simulation or testing, the HIL capability of real-time simulators allow the design and operation of microgrid control, protection, and power devices to be evaluated under realistic operation conditions before they are deployed in the real-time or actual microgrid system. Now, this is one of the case study. Let us assume a system architecture. So what we do, we have a microgrid connection where you have a bus, which is a three-phase 480 volt, very, very low voltage grid. And you have a point of common coupling. We have a lithium-ion battery. We have a diesel generator. We have a AC load, and we have a PV. Okay, so this is so-called AC microgrid, one of the simplest architecture, where you could see the load is going to be 0.5, and you have diesel generator which is 1.25, and PV which is actually of 0.4 megawatt. All right. So it is something that at a given point of time, the diesel generator which is feeding to the grid, PV is feeding to the grid, load and battery. Battery is bidirectional, rest all are actually unidirectional. So when you see mode of operation, one is actually grid connected mode, just to understand once again, before we go for PHIL. In this mode, the grid supplies the power requirement of the load, where there is no power from the PV or battery. When there is no power from the PV or battery, how many components we have? We have a battery, we have a PV, we have a diesel generator, we have a grid, we have a load. When PV is not there, battery is not there, then the power will come from the grid to load actually. The PV always operate with MPPT, that job is done. Battery either operate in charge or discharge based on the reference command. Diesel generator may help in voltage regulation by controlling its excitation. Okay, so you can use that as a voltage regulation. In case of isolated mode, in this mode, grid is not available. The PV may or may not operate in MPPT. When the grid is not there, you have to derate the PV. No, sometimes it will operate in MPPT. You cannot force it now. So it may operate, may not operate with MPPT. Battery either charge or discharge based on the reference command. The diesel generator is operated in synchronous mode and provide the voltage and frequency control in the islanded microgrid. So what your bus has provided, B and F, now the diesel generator will provide you the same thing, right? So that's what I wanted to highlight. Either you should have a battery or a diesel generator to make sure that your PV, operate in a isolated mode, islanded mode. Okay. So then we move to inverter control of PV and battery. The PV and battery controls are based on decoupled PQ, that is real and reactive power mode control strategy with internal startup and protection logic blocks. The PV and battery sources are interfaced to the AC grid using dynamic average model of the DCAC voltage control converters. Dynamic average model of DSC do not represent the high switching frequency dynamics, reducing the computation requirements and allow higher simulation time step for modeling large microgrid cases. This is the architecture, as you could see, PQ control, very basic. Now, one important part of digital generator, as on today, we haven't talked about a digital generator, and you'll be happy to know our admired lab to have a digital generator. So you have seen the live, no? I will also, one of the video you will see. So we are not limiting. So what you have seen in the lab, we have seen a DC microgrid, we have seen a AC microgrid, and especially PV and wind. We have seen PV emulator, wind emulator, then we have seen battery, and then battery charge, BMS and charger. So there are 4 things we have seen, but many more things we are going to see in due course of time. So first of all, speed governor, which helps to regulate the speed and frequency of the diesel generator by changing the mechanical input of the synchronous machine rotor. An excited system helps to regulate the terminal voltage of the diesel generator by varying the field current through excitation systems, overexcited synchronous generator, underexcited synchronous generator, normally excited synchronous generator. For different power factor and power system applications can be used. In the first case, actually inject reactive power into the system. Second, it observes the reactive power. And third, it operates at the unity power factor. So if I like to simulate the previous system, there are 4 cases I can create. All of you please remember, then I'll show you the simulation results. So the case 1 where no distributed energy resources such as PV, diesel generator, battery in the system, nothing is there. Simply load and grid, okay? The second case, no DR in the system, but the load is now changing from 0.5 megawatt to 1 megawatt. So there is a sudden load change. We'll see what is happening. The third case, DR switched on and battery set in the charging mode. Well, DR is on, battery is in the charging mode, okay, and it is a off-peak hour. Okay, so PV operated in MPPT, diesel generator operated in the voltage regulation mode, that is overexcited mode. So what is the case 1? Please repeat. No DR. Case 2, no DR, but load increased from 0.5 to 1 megawatt. Case 3, DRs are actually switched on. Okay, battery started charging and PV is in an MPPT. The case 4, DR switched on and battery set to discharge mode. That is the considered to be a peak mode, okay? And PV insulation decreases operating MPPT, okay? And then diesel generator operated in voltage regulation. Point 4, I'm repeating again, DR switched on, battery set in discharging mode, PV insulation decreases operating at MPPT, diesel generator operated in voltage regulation. So mainly the battery actually discharging in the 4th case, where the 3rd case actually the battery is getting charged. So then we will have an isolated mode. Islanded mode of operation, there are 3 cases we will consider. There are 4 cases, grid connected, and 3 islanded mode. Case 1, main grid is disconnected, battery is charging, PV at MPPT, and diesel generator regulating the voltage and frequency. Okay, case 1 of islanded. Case 2, main grid is disconnected, battery started discharging, PV at MPPT, and diesel generator regulating the voltage and frequency of microgrid. Case 3, in continuation with previous case, additional load switching occurs from 0.5 to 1 megawatt. Means you have a islanded mode of operation, and in that again load increased, which is very, very unrealistic. Grid is disconnected, load is also increased in islanded mode. And power balancing, you have to, only way is to do the diesel generator actually, you have to operate it. So we'll see wonderful simulation results. So these are all your, RSCAD simulations and grid connected. The number 1, you can see the PCC voltage, we can see the breaker currents, and you can see the grid current, generator current, PV current, and battery current. Right side is more important, very smooth, all 4, isn't it? So PCC voltages you could see, currents you could see, And especially the battery current, PV current, generator current, grid current, that they are the signals actually, This is how we can simulate. So I do not know, do you have access to RSCAD? But even if you do not have RSCAD, I will strongly recommend you can go to PSCAD, which is economically and possible to get access. The similar result you can even produce in PSCAD. You need not invest crores of rupees. Simply go with the PSCAD software. Everything is possible. Okay. Now moving to case 2, you see there is a load switching. Could you see the PCC breaker current? It started and suddenly the load increased, the breaker current almost doubled. Okay, PCC voltage you could see here. Is it fine? You could see there is a battery, there is a PV, there is a diesel, there is a grid, and there is a load bus. So this is how actually we model in real-time simulations. And this basically you've done it at RTDS. But yeah. When in RTDS literature, if you go, these examples they've already explained. Everything is available. You can reproduce it or you can use the study actually already. And then moving to case number 3. So you could see battery, PV, generation and load. Moving to case 4, grid connected mode. These are the scenarios. All right. Now, if you go to isolated mode, now the situation become interesting. The grid completely lost. All right. So you could see that islanded block, the red block. The previous grid is actually black. Am I right? Grid connected. So that switch actually in the simulated version, you can move to islanded mode, means it is disconnected and it will start simulating. All right. You can experience the second one. You can experience the third one. Right? So this is how actually, so what we have learned today, how to carry out actually simulation in a RTDS platform for 7 different cases, 4 for grid connected mode and 3 for islanded mode. So dear students, today is considered to be a stressful class because this is what very interesting to see in online, but when you experiment this, more excitation can happen. If you do not have access to RTDS, I will strongly recommend you will be having access to PSCAD. At least PSCAD, you create those current sources, current responses, current waveforms for your PVs, for your diesel generators and batteries, and experience the whole concept. With this note, we come to an end. So thank you very much, and wonderful talking to all of you and patient hearing. Bye-bye. Take care.
Thank you, sir. So any query from any of you? So if you have any query, just type in chat. We'll make you one note.
So they're saying thank you. So means no question, it seems to me. You can now brief about the examination.
Okay, so
all are requested not to exit from the meeting. I think Dr. Manmohan Garg will explain you the process of, Scott, it is a test, quiz test. Okay, please listen to him carefully.
okay, so
We can stop sharing so that, the
एंड नहीं करना है स्टॉप शेयरिंग वापस जाओ विवेक्स पे स्टॉप शेयरिंग वाला ऊपर आता है ना सर किस होगा Okay, so in the email which you have received very first time, where you go to this Canvas registration link, and we mentioned that. So this is certification course. So for certification, you first need to have attendance, and then 2 quizzes will be there. So one quiz after 10 lectures, then another quiz, after further 10 lectures. So today we will have quiz on our lectures, which was conducted from day 1 to day 10. And there are 30 questions in this quiz, and you will be given 30 minutes for that. So this quiz we will post after at 6:30 on the Canvas. So you have to go to Canvas and you access it from there. So you can start it. So you can start it anytime you wish. We will keep it open for 2 days. So by Saturday and Sunday, including today, by Sunday night 12 o'clock, you can submit it. So whenever you feel that you have a time, not necessary you attempt it right now only, maybe tomorrow, maybe day after tomorrow, but please submit it by Sunday night. So whenever you feel you have enough time, because once you start it, you have to finish it in 30 minutes, right? So that after 30 minutes, it will be automatically stopped. So any 30 minutes you can choose and then you can start when you have a stable network. Please make sure that you have a stable network so that all questions you can attempt. And after that, after end of this program or schedule also we have attached on the website, we will have second quiz. So yeah, so this quiz you can access through Canvas only. So I hope most of you have already made account on the Canvas. If not, then please check your email where you have got the confirmation of registration for this course. In that we have sent you link to join Canvas, and also we have attached one PDF that how to do registration on Canvas. So if you have not done, you do it today, then you can attempt quiz tomorrow. So that is mandatory. If you do not attempt the quiz, you do not appear in the quiz, then you will not get certificate. So please do so. So you will soon get it. Questions comes from all lectures till date. No. So the questions will be there up to date 10 lecture. Quiz not visible. Yeah, it will not be visible because we have not published it. So we will publish it 6:30 or maybe 7 today. And after that, it will be accessible to you. It will not be accessible right now. I will put the message in WhatsApp group also as soon as it is published, and then you will be able to access. If you face any difficulty, you can write an email to me or you can put your query in the WhatsApp group itself so that we will connect you one-to-one and will resolve your queries. Quiz one also not given. Yeah, that's the quiz one only, madam. So this is for quiz one we are talking about. There will be total 2 quizzes. This is quiz 1, which includes the materials from lecture 1, day 1 to day 10, right? Then day 11 to day 20. And the schedule is also published on website, or I will share in a group also. So you will come to know day 1 to day 10. So I request that these questions are framed very carefully, whatever sir has taught to us in all those lectures. So you can just revise the PDFs which are already available on the Canvas. Then after that only, if you attempt the quiz, then you will be able the good score. And based upon the score you receive, you will be getting the grades for this course. So wish you all the best. For further queries, you write me email or sir, please publish that soon so that we can attempt it now only and we want to stay free on weekends. Yeah, sure. So yeah, we will publish it. So you can attempt it today itself, no issue. So thank you. Okay, so as you know that we missed few lectures in between due to such urgent meetings. So one we have already covered last Saturday, and one we are going to have tomorrow. So sir has given his consent to have a lecture tomorrow. So tomorrow 5 o'clock we will have a lecture. Also, please note that attendance are mandatory for getting certificates. So sometime I feel that attendance should be more than it is whatever it is right now. So please attend all the lectures if set attendance are very short. Yeah, for your benefit, yeah, you will be learning a lot here. And now this, we are moving towards the last week of course, so it will be more interesting. And whatever, as today also you have seen that whatever we learned in previous classes, if you have missed it, then sir has revised that.
I mean, slowly we are moving into, you could see, the pace of the course is slowly keep on changing, We started with stories, jokes, and then bit of diagrams, complications. You do attend the better perspective. Very good. I think Chandrasekhar is excellent. So now you can see today we entered to simulation, and then you will see the PHIL and demonstration, and finally the deployment of megawatt scale. So it's a very good journey. Thank you very much. Yeah.
Okay, so we will publish it soon within 10 minutes. Okay, thank you.